Okay, so we are continuing our journey on machine learning and different resources that are at the heart of machine learning. And now we're talking about optimization. So optimization is at the heart of machine learning. If you remember in the previous meeting, a guy solved an exercise in which the concept of a model appeared. So the concept of a model was, if you remember, there was like a linear model, and there was also a quadratic model, and we were searching both spaces of all possible linear models or all possible quadratic models, and we're trying to find to generalize, to find a good relation that represents the data. And it was clear that within the model of the linear, there were no good explanation. You had to go to the quadratic model in order to get a good explanation for the data. So that was last time, and it's important to understand that that's just a very simple example of the general phenomena in which we search a certain model or search a certain search space to find an optimization of a certain objective function, which hopefully will give us a good generalization or will behave well on new data. And that's typically the objective of machine learning. So in order to build some intuition about optimization problems, I'm going to give us go through a very general statement about optimization that we'll see will be helpful later on to frame a lot of the things that happen in search, in numerical search algorithms that have to do with optimization. So the idea is that I'll draw a little picture here. So basically, we have some space. We're trying to search, and in our case, it will be a vector of n numbers. And there's some subspace here, in which the desired behavior or the optimal behavior happens. Like for instance, think about it as a minimization problem. So this set that is unknown to us is the set where everything is minimum. Or think about a root of a function. So this is the point where the function is 0. So think about the points for which the function is just doesn't change. Okay, so it could be something. It could be the points. So O could be like the points where the function is stable, doesn't change, or the points where the function is the smallest. Or maybe even the points where the function is 0. Doesn't matter. So we have this subset that we're searching. And we're starting from some point. This is our starting point. And then we have some algorithms that takes us to another point. And so on. And at the limit, it gets to a point. So what we are interested is under which conditions those points are going to be in the desired subset. Okay. So the idea of the formulation that I'm going to give now, which is a very general formulation, is that if I have a certain that this is whenever I'm outside of the special subset that I'm interested in, then that kind of guarantee under certain conditions that I'm going to get to where I want to go. Imagine a hill. If you're at the top of the hill and you're always going down, you'll get to the valley, or vice versa. If you're at the top, yeah, okay. So if you want to go up and you always go up, then naturally you'll be going up. So maybe you'll get to the place that is the highest. Maybe not the absolute highest, but somewhere that is high, because you're always going up. So that's the basic intuition. Now let's cast it in mathematical. So what I'm in a mathematical formulation, it'll be a very general framework that we'll use throughout our discussion of optimization, numeric optimization. So let me spell out what I'm assuming here. So one thing is I'm assuming that I have some function that is going down. Let's say I'm focusing on going down. So this function, whenever I'm outside of the set that I want to get to, I'm actually going down. Okay? So the algorithm is going to take me down, strictly down, whenever I'm outside whenever I'm outside outside the set I want to get to. So I'm outside. If I'm outside the set I want to get to, then z is going to become smaller. Okay. Now, if I'm inside the set I want to get to, so for points that are inside the set I want to get to, then z is going to maybe not become smaller. So it's going to be less than or equal. Maybe it's even equal, but maybe it's going just okay. And the only other assumption is that if I have some series of points in Rn that converges to x, then the algorithm applied on that point converges to a of x. This is correct whenever a is continuous, for instance. So a is essentially a function from a Rn to Rn. And it meets these requirements. And Z also meets these requirements. Then what I'm going to say is that this series is going to converge to the set O, if it converges. Okay, so my claim is that if you look at the series x1, a of x1, and then apply a twice on x1, and so on. And if you assume this converges to x, then we claim that x is going to be in the optimal set. Okay, so that's the setup. Any questions on the setup before I show you why this is correct? Okay. So let's see why this is correct. It's actually nice and simple, but very useful when as a general framework. So why is this correct? So one observation here is that if I look at the following series, A1, A of x1, A square of x1, and so on. Can you tell me where it converges to? Assuming this. So assuming x and a of x and a square of x converges to x. Where does a of x1, a square of x1 converges to? Question mark. Any thought?
Is it just the pair XX? If they wait, so you're saying each of them individually converges to X, right?
No, I'm saying the first series x1, a of x1, a square of x1, and so on converges to x. And then I'm asking, what does a x1 is the first element of the series, a square x1, so on, what does it converge to? You know?
Why isn't it just X like the other one? I'm not sure what you're asking, Eitan.
Yeah, that's the answer. That's why you're not sure.
Okay.
That's the correct answer. It's like if someone comes to you and say, 1/2, 1/3, and so on, converges to what?
0.
0. Now, what about 1/2 and 1/3, and so on?
Yeah, same.
Same, converges to 0. Any finite number that you remove from the series will not change what it converges to. Okay. So yeah, so this is a crucial observation here, because you saw that I made the assumption that this converges to AX, right? So this converges to X, but it also converges to what? According to my assumption.
AX?
Yeah, it converges also to AX. So we have that AX and X are actually what? What is the relation between AX and X? So this series converges to X, and the same series converges to AX. So what's the relation between AX and X?
They're equal.
They're equal. You can't have two limits. There's only one limit to a series, if there is one. Okay? So it turns out that AX equals X. So, okay, very nice. So if AX equals X, what do we know about ZX and ZAX? They are
Equal.
equal. So it means that it's in the optimal. Therefore, X is in O. So these are equal. And therefore, X is in O. Because otherwise, if X is not in O, then we're going down explicitly. Okay? So it turns out that if the series converges, it converges to our objective of the optimization. And that's a very general statement. And also, you can, after the meeting, you can go to the appendix here. I sent a link, and you can try and read it here. It's written more, it's written here as well in a formal way. And essentially, this framework is a framework that will apply for us throughout the numerical optimization. It will apply to all of the techniques that we will be applying in machine learning, the gradient descent, Newton method, everything we talk about in machine learning will have a stage where you'll have an optimization problem, and then you'll be playing around with this observation. Okay? Any thoughts or questions about this? Okay, So thank you very much for joining today, and we'll continue next week. Bye-bye.